All right, awesome. Thanks, Dean, and thank you for that introduction. Just a little more about myself. Like Dean said, I'm the VP of Business Development with Sustainable Systems here at Price. I've been in the HVAC industry for about 20 years. 15 out of those 20 have been at Price in various different roles. One big thing I would point out is I've been involved in a lot of different types of projects, different applications across the continent as well. So hopefully that brings in some value to this conversation. Like Dean said, we feel the conversation is very relevant in terms of what's happening with energy codes and generally what's happening around us and all the questions we're getting from our clients, customers, and everyone else. Anything we could do to support it is what we're here for. So yeah, please keep it engaging. Please feel free to add in those questions as need be, and we'll address them during or after the presentation, like Dean said. So we'll keep moving along here in terms of the agenda for today's presentation. What we'll do is we'll start with HVAC energy code and local law trends. Essentially what's happening with our energy codes, what's happening around us. There will be a little bit of a conversation around the stretch code in Massachusetts as well. And then we'll get into low lift systems. When we talk about low lift, essentially what it's referring to is low compressor lift, which we're obviously not into chiller manufacturing ourselves here at Price Industries, but obviously those are something that are used very readily on HVAC systems and are required for cooling and now for heating as well in the form of heat pumps. And we feel that plays a big role in terms of where we might be going and how decoupled sensible cooling systems complement those types of systems and work well with them. So we'll spend a little bit of time talking about low lift, and we'll get into decoupled sensible cooling systems. That's where the plot may thicken a little bit, so it'll only be for like 5-10 minutes where the content may get quite a bit technical, but I'll try and go slow during that part of the conversation. But again, feel free to ask questions so we could expand on it. And once we've gone through some of the common applications and common ways of creating decoupled sensible cooling systems, we'll then get into control strategies addressing zone temperature control, airflow control, and space humidity and condensate management. All right, with that, we will get started. So starting off with energy codes, when you think about energy codes for HVAC systems, the first code that comes to mind is ASHE 90.1. Now I know in Massachusetts, it's the IECC code. That's usually what's required and applied, but they go hand in hand, and there are a lot of similarities between the two codes. And essentially the point we wanted to make here was, if you look at 90.1, which essentially came into existence back in 1975 with the oil embargo, and you can see for the first few years, there wasn't really much that has changed in terms of the energy usage through our HVAC system. That's where the standard goes, except for one time when there was a reduction in the energy usage through the HVAC system. But essentially, over the last 15 to 20 years, where we have seen most of the changes, essentially what the standard has done is they've made a point now of updating the system every 3 years. So essentially, the standard committee meets every, they meet a lot more often than 3 years. I think at least 2 or 3 times in a given year, to work towards a newer version of it every 3 years. And the point is to make it more and more stringent as we go on. To give you guys an idea, if you compare the 2019 version to the 2004 version, there's roughly about a 40% drop in the amount of energy that you're allowed to use through your HVAC system if you were to comply with 2019 versus the 2004 standard. So that's a little bit about 90.1 and the energy codes in general in terms of the trend, the direction that they're moving towards. The same applies to the IECC code as well. Now, the other question is, what's happening across the country in terms of the adoption of these standards? There's different versions, but where are different states in terms of adopting these standards, and creating stipulation in terms of what's required in their given jurisdiction. So what you see on screen is where things were back in December 2018, and kudos to Massachusetts and a lot of the other northeastern states. What you would see is West Coast and parts of New England, Northeast is where most of the greener adoption was, while the rest of the country was lagging behind a little bit. Fast forward 5 years, you can see how things are changing. The states that were green to start with are becoming greener, and other states across the country are also starting to adopt greener versions of these codes. So that's a little bit about the adoption of these codes. One thing you'll notice, this map shows 90.1/2019 as the version for Massachusetts, and again, we'll talk more about that as we go on in a couple slides. Excuse me. Electrification, that's something that's a lot more recent. Electrification, I'm pretty sure most of you guys are aware of what it means. I'll just, provide a quick explanation of it. It doesn't mean that you are now required to use electric heat, electric resistance heat, instead of fossil fuels to provide heating within the building. The point is to not bring any fossil fuel into the building itself, right? So there are other ways of providing heating, for example, heat pumps, which is a lot more efficient than using electric resistance heat, right? So again, necessarily, this doesn't mean electric resistance heat. What it means is basically electrifying your building so there's no natural gas or fossil fuel going into the building. And you'll notice there's a very similar trend here as there was with energy codes. A lot of these mandates are coming on the West Coast and Northeast part of the country, and we feel that's something that's going to spread across the country as well. So that's a little bit about, again, at the higher level across the country, what's happening with energy codes and electrification. Now, if you look at Massachusetts, you guys are probably familiar with this. The code has, or the state has adopted a tiered approach here. Essentially, as a base code, excuse me, you're required to use IECC 2021, which is what compares or translates closely to 90.1/2019, which is why the map showed 2019 there, right? But the other two tiers is where, essentially there's larger adoption, and a lot of it is driven by the Green Community Act in Massachusetts. And essentially what it means is the next tier up is the stretch code, which is stringent compared to the base code, so stringent and 90.1/2019. And then you have the specialized code, which essentially is close to the net zero code. And then, the towns and cities have the ability to vote on these codes to see which one they want to adopt. And if they would want to be a green community, then they're required to have at least a stretch code as an adopted code for their jurisdiction or community. To give you guys a quick snapshot of what's happening across the state, this is what the map looked like about a month and a half ago, March 12, 2025. And essentially what's shown here is 85% of the communities across the state have adopted either the stretch code or the higher version, which is a specialized code, as a requirement for their community and for their jurisdiction. So it's pretty evident what's happening, and clearly Massachusetts is at the forefront, both from the energy code and from the electrification side of things as well. And we'll talk a little more about certain specific items that might be relevant within the new code, especially the stretch code, as it relates to decoupled sensible cooling systems as well. One last thing before we move on. The next section is MEP 2040. So this essentially is a version, the MEP version of Architectural 2030, if I could say that. Architectural 2030, you guys might be aware, a lot of our architectural firms, they were signatory to it, especially some of the more progressive, bigger architectural firms. And essentially the idea was to start to become, net zero by 2030. Since then, that happened 15, 20 years ago. Since then, the scientists have found out that, essentially that's not an aggressive enough goal. So what they are now saying is, we basically have to become net zero by 2040 to have even a 50% chance of not getting to an irreversible point with climate change or temperature increase. So that's what MEP 2040 is all about. This is all driven by MEP consultants. And it's not just about operational carbon, it's also about embodied carbon. So there's something to note in near future, what we would expect is, for specifications to change for HVAC products, whereas manufacturers, we may have to start provide providing EPDs for our products so you guys could calculate the embodied carbon for the HVAC system that you might be designing. All right, so that's a little bit about trends in terms of what's happening. Let's move into the low lift side of the conversation. So I'll jump a screen here. What we're looking at is the refrigerant cycle. We're not going to go into the weeds of the cycle itself. I'm sure most of you guys are familiar with this and have understood and known how it works, at least at a high level. What we need to understand here is, essentially, if you look at this area in gray around this black rectangle, that essentially represents how much work your compressor has to do to provide a certain amount of cooling, right? So what it means is, essentially what you look at here is there's two different temperatures that it's dependent on. One is your ambient temperatures. For example, if you're using an air source chiller, whatever your outdoor temperature is, in Boston, it might not get as hot as 110, but whatever the ambient temperature is what would dictate, how much work the chiller has to do. What also makes a difference is the kind of water that you're supplying into the space. If you're supplying 42-degree water, say to your air handler or to a fan coil, that would have an impact on how much work that has to be done to provide cooling in that building or within that space. Now, I think in most cases, when we're looking at these projects, we generally compare your air source chiller to a water source chiller. And essentially, and most of us understand that water source chillers are more efficient than air source chillers. And the reason is, again, on the ambient side, you're dealing with milder temperatures. When you use a water source chiller, say with a cooling tower, the water that it's exchanging heat with is a lot more milder than the ambient condition, right? It'll be colder in case of cooling compared to what it will be for on the air source side. And that's why a water source chiller takes less energy to condition or to provide the same amount of cooling, right? That's what makes them efficient. So that's typically what's considered. What's not always considered is what's happening on the space side of things, right? So, like I was saying earlier, what you send to your space also has a big impact on the efficiency of your chiller or your compressor, and that's what we're trying to show here. So in other words, if you use a decoupled sensible cooling system, for example, chill beams, now you could get away with supplying 56-degree water into the space, and that makes your system, at least your plant, that much more efficient. And that's essentially what low lift is, working with milder temperatures instead of pushing it to the extremes just because you could create colder water. That's how you make your system more efficient. One chiller manufacturer, he shared a good analogy, with us. Essentially, what it is, as a biker, if you're biking uphill with the wind in your face, that's what's happening when you're dealing with standard lift. In low lift, that same biker is going downhill with the wind behind his back. That's how the compressor feels when you're using a lower lift system, and that's essentially what makes it more efficient and helps it last longer as well. So that's a little bit about low lift at a conceptual level. What can you expect on your project? So this example is from a large project, roughly about 500,000 square foot office headquarter for a financial firm. This is actually in New York City. And essentially what they did on this project was they used two different chillers. 42-degree chiller was used to provide water to the DOAS unit to dehumidify the air, both for outdoor and space load. And then 55-degree water chiller, a separate chiller, was used to feed chill beams all around the perimeter of the building to provide cooling. Essentially what they found was their cooling efficiency was 26% higher, going from 42 to 55. And the rule of thumb there is, essentially for every degree that you walk towards the milder temperature, you gain 2% efficiency at your cooling plant level. That's the cooling side. Now, similar results could be expected on the heating side as well. This table comes right out of ASHRAE 90.1 2019. It's the heat pump efficiency requirements table. And essentially what you'll see here is if you go from 140-degree water to 105-degree water, you gain 27 to 30% efficiency for the heating side of your plant. Essentially, the point we're trying to make here is you'll probably hear similar conversations from your heat pump manufacturers as well. Just because you could create 140-degree water doesn't mean it's the right thing for the project. Sometimes the right thing is to go as mild as you can, as long as there's equipment available in the space to use that milder temperature to provide heating for your space. And that's where, again, decoupled sensible cooling systems come into play. And we'll talk about that in terms of how those systems can work with really low temperatures like 105 or lower to effectively still provide heating within the space itself, right? So that's the cooling and the heating side. Now, generally, the question that we get at this point is, if we're providing milder temperatures or lower lift, then our delta T at the plant level must drop and we must need more GPM. So what does that do to the overall efficiency of the system? Because you need a bigger pump to pump all that water into the space. Here's an example. What we're looking at here is, let's say you have a system, a standard lift system. We're using 42-degree water with, for argument's sake, 12-degree delta T. I know that could change from project to project, but this is more for illustration purposes. And then let's say on the lower lift side, to kind of create a worst case scenario, you're using 56-degree water, and let's say your delta T is half that if it would be for a standard lift system. Now, because your delta T is half and you're providing the same amount of cooling, what that means is that your GPM will double. You'll need double the GPM, and essentially you need slightly bigger piping with low lift, but even with slightly bigger piping, essentially what that means is that your pump horsepower will double as well, right? So your pump horsepower went from roughly just about 3 to 6.3, right? Now, the bigger point here is, even though your pump horsepower doubled, your pump horsepower is only a fraction, generally 3 to 5% of the overall chiller horsepower. So even though pump horsepower is doubling, given the amount of reduction, 26% on the chiller horsepower side, your overall peak horsepower is still substantially lower, 23 to 24% lower compared to a standard lift system, right? So that's kind of the point we wanted to share here in terms of just comparing the overall peak horsepower of one system versus the other. Okay. Lindsay, any questions at this point before we move to the next section?
No questions so far.
All right, awesome. Thank you. All
You're
right,
welcome.
Yep, thank you. Decoupled sensible systems, we'll get into the discussion for those systems at this point. So essentially, if you think about your typical overhead all-air system, sometimes also referred to as a VAV system, what's happening there is you've got all your heating and cooling at the air handler, and you're using air to bring all of that heating and cooling into the space. With a decoupled system, like Dean said earlier, you're decoupling, apart as much as you can of the sensible heating and cooling and doing it in the space instead of doing it at the air handler and then using air to bring it into the space. Why do you want to do that? Well, the big reason is because water is a lot more efficient at transporting BTUs compared to air. Specific heat of water is as much as 10 times that of the air. Essentially, what that means is the amount of horsepower you need to transport the same amount of BTUs from one place to another is substantially lower with water compared to air, right? So for argument's sake, you had a chiller, you're pumping all that water into an air handler and using air to bring all that cooling into the space. Instead, if you could take part of that cooling directly into the space, now you're bypassing the fan, reducing the size of the fan itself, the fan horsepower, and then using pump horsepower, which will be a fraction of it, to provide cooling within the space. The other thing it does is water takes a lot less space to, again, transport the same amount of BTU. So what you're looking at here is, for a system that would have needed an 18 by 18 inch duct to, using air to provide all the cooling, you can get away with 1/2 inch pipe and 7-inch duct to provide the ventilation and the cooling within the space itself. Right, so that's kind of what the decoupled systems are at a high level. What are some of the decoupled system types? First one is chill beams. An active chill beam essentially is a sensible only device that provides heating and cooling at the space level. And the way it works is you have primary air coming in through your dedicated outdoor air system. and that primary air goes through a nozzle, which creates negative pressure behind the coil, and that's how you induce air from the room side. And essentially, just we were talking about low lift systems, chill beam systems like low compressor lift type temperatures. So generally speaking, chill beams would need 56 to 57 degree entering water temperature. The reason for that is your space set point is 75 and 50%. We'll talk a little more about that as we go on. And that typically means a 55 degree dew point in the space. And you want to keep your temperature 1 to 2 degrees above the dew point just to keep the system with sensible cooling or avoid heating in the system. Avoid condensation at the coil itself. On the heating side, again, going back to heat pumps, chill beams always liked milder hot water temperatures. You can imagine, given the amount of coil surface area that you have at these chill beam systems, there's a lot of heat transfer that happens. Generally, it's not recommended to have really hot water going to these chill beams because your discharge air temperature will be way too high for the air to come into the space. You'll end up stratifying at the ceiling level, right? The chill beams always like lower entering water temperatures when it came to heating, and now it's becoming an advantage because that works well with heat pumps because heat pumps like these lower temperatures when it comes to heating systems themselves. In terms of induction, these chill beams, they come with various different nozzle sizes, and that induction ratio could be anywhere from 2 to 6. As an example, if your induction ratio was 3, what that means is if you have 50 CFM of primary air coming in through the duct system, roughly about 150 will be induced over the coil, and overall there will be 200 CFM being moved within the space itself. That's generally how the air movement happens, and that's a good office or commercial space example as well. Generally, you could see your airflow requirements, like if you had 1 CFM per square foot that you needed to condition an interior space, you're using an all-air system. With chill beams, most likely you'll end up needing, 1/4 or 1/3 of the airflow, for your ventilation and your latent capacity, and that's where you'll end up using an induction ratio close to 3 or 4 for an office application. What are some of the chill beam products? What do they look like? Here's a ceiling chill beam. That's what you see the cross section of here as well. The space is exposed, comes in various different lengths from 2 feet all the way up to 10. It could be floor mounted beams as well, very popular with schools, especially in classrooms, because they discharge the air at the low level. These are not induction units. They don't discharge up top, they discharge at the low level, which provides displacement effect within the space. They're very quiet, especially even compared to induction units, and provide quieter operation. And they can come with heating options up top as well, including fin tubes at the top of the cabinet. Recessed chill beams, essentially what this is it goes into a recessed ceiling. So imagine a linear diffuser in the ceiling. Typically that linear diffuser would have a plenum behind it. With a chill beam system, you replace the plenum with this recessed chill beam. Essentially all you see from the space side is just a linear, generally used for your perimeter applications or architecturally driven spaces where you're after a certain look or the architect is after a certain look. This way, essentially the entire chill beam is again recessed behind the ceiling itself. And last but not least, like I've said earlier, primary air has to take care of the latent load as well, which again we'll talk about that in a couple slides to expand on that further. So how do we make sure we achieve an effective or an efficient chill beam system? That's where transfer effectiveness comes into play. It's defined by ASHRAE 200. That's the standard that dictates how we need to test our beams as manufacturers. So essentially, what transfer effectiveness is, if you think about an all-air system, this is where you have roughly about 20 degree delta T. So 75 set point in the space, 55 is your supply air, 20 degree delta T translates to roughly about 20 BTUs per CFM of air coming in through the air handling unit. With chill beams, the more you transfer that BTUs over to the water side, the more effective the system is. In other words, more BTUs you could create per CFM, the better. So typically with chill beams, your transfer effectiveness, which is how many BTUs you are able to generate, bring into the space per CFM of primary air, the better the system is. And generally, the rule of thumb is to be between 60 to 100 BTUs per CFM. In other words, 2 to 5 times more BTUs per CFM of air coming through the central air system compared to an all air system. So as an example, if you had primary air coming in at 55 degrees, that's again roughly 20 BTUs per CFM, because again, your set point in the space would still be 75. And then rest, which is 40 to 80 BTUs per CFM, is happening at the coil itself. And again, this CFM is, the primary air CFM. So the additional 40 to 80 is added at the coil, and that's again how you make your system more efficient and transfer that cooling over to the water side. So that's a little bit about transfer effectiveness and how you could make sure that you design, an effective and an efficient system. It's moving towards your space latent load. Some of you guys might be wondering, going back to my office example, we're going from 1 CFM to say 0.3 CFM in the office space, but your space latent load has not changed. The number of people that are there has not changed, and they're adding latent energy to the space. How do you take care of that with a lower amount of primary air that's coming in, since the cooling coil of the chill beam is only doing sensible cooling? So let's look at some of the facts in terms of what's happening within the space. So let's say our set point is 75 degrees, 50% RH. That translates to a certain amount of moisture. If we're talking about grains per pound, it's roughly about 65 grains per pound. That's how much moisture you have in the air that's within the conditioned space, right? Now let's zoom in and see what happens when we bring air in through different systems, right? So again, that's your space condition, right? If you're using an all air system, typically what you'll do is you'll supply air at 55, 54. That means a certain amount of moisture depression, typically roughly about 3 BTUs per CFM, right? And let's say you're supplying 1 CFM per square foot. That provides the amount of latent cooling that you need for the occupants in the space itself. Now, if you were to design the same project around chill beams, what would happen is the primary air that's coming in, you will have to create a larger moisture depression. So instead of supplying the air at 55, 54, we'll supply it at 55, 51. What that means is your latent capacity per CFM is 3 times. Again, that moisture depression is larger, which means latent capacity is higher. So even though you're supplying 1/3 of the airflow, you've got 3 to 4 times more the latent capacity, and that's how you make sure you're still taking care of the latent capacity in the space itself. And essentially, in a nutshell, what it means is your DOAS system has to be sized, so that small amount of airflow that you're bringing in, it has enough moisture depression to offset the latent cooling in the space itself. So hopefully that makes sense. Essentially, that's what you need to keep in mind when it comes to space latent load. Now moving on and trying to understand what are some of the good applications with these systems. That's where sensible heat ratio comes into play. And again, this is a section I was talking about where I'll probably thicken a little bit in terms of the technicality of the content. I'm assuming most of you guys are aware with sensible heat ratio. Essentially what it is the amount of sensible heat load that the space has divided by the total heat load, right? So ratio of what percent of your load in the space is sensible heat load. And what it means is higher the number as you go towards 1, lower is the latent content, right? 1 means 100% sensible load. There is no latent in the space. And think about a data center. And they get very close to 1 as your sensible ratio. As you get closer to the lower fraction, say 0.2 or 0, that's where your latent load is dominating, right? I can't think of, a 0 as your sensible heat ratio type application. What that would mean is 100% of your load is latent load in the space. There's not many applications that you get like that, right? But that's kind of what the idea with sensible heat ratio is. Why are we talking about sensible heat ratio here? The reason is because sensible heat ratio, especially when it's driven by people load, which will be the case in most applications for a given location, for example, Boston at that location, or a certain application, As you change the number of people in a given space, that changes your sensible heat ratio. And what it also does is it has a direct impact on your primary airflow, right? So for example, classrooms, if you think about a classroom application, which is a lot more densely occupied, sensible heat ratio is lower, generally around 0.7. Latent load is higher because it's more densely occupied. And your typical primary airflow requirement is 0.4 to 0.6. Compared to office, where you're not as densely occupied compared to a classroom in a school, your sensible heat ratio is generally around 0.8, 0.85. And your primary airflow requirement is typically 0.1 to 0.3 CFM a square foot, right? And that's how sensible heat ratio kind of dictates how much primary airflow is coming in. And we just talked how primary airflow is a good indicator of if you have size and effective chill beam system, an efficient chill beam system. And a typical rule of thumb, there is applications that have primary airflow requirement around 0.1 to 0.7 CFM a square foot are generally good applications for chill beams. And to expand on that a little more, again, if you look at this protector representing sensible heat ratio, this is what represents, this arch is what represents 0.7 to 0.9 sensible heat ratio. And typically the applications that would fall within this range are these applications that you see on your screen, your classrooms, patient rooms, courthouses, libraries, computer rooms that are attached to office buildings, correctional facilities, offices. These are the applications where we mostly see chill beams in, and they tend to be good for chill beam application because this will ensure that you have a system that provides higher effectiveness and higher energy efficiency when you're using chill beams. Now, what happens, when you're outside that range, for example, if your sensible heat ratio was higher, for example, data center, in that case, your sensible load may excessively drive how much primary airflow you need to condition that space. And it may or may not make sense to use chill beams in that application. Whereas on the other side, when your sensible heat ratio is lower, on the lower side, that's where, because you have a lot of latent load may excessively drive the primary airflow and hence make the system not as efficient as you would have liked to. One thing I would say is this range is a guideline. Just because you're at 0.96 doesn't mean it's a bad application or a 0.69. It all depends on, again, what the overall transfer effectiveness looks like. And sometimes what we find is you have a larger space, excuse me, where one or two zones might be outside of this range, but majority of the project is within this range. It may still make sense to use chill beams in that application. So that's a little bit about applications and where chill beams make sense to give you guys an idea in terms of what to expect. Offices, you can expect around 30% energy efficiency compared to baseline or your all air systems. Now, most of this, in fact, all of this is coming from just the fan side. In fact, let me take that back. Not all of it, most of it is coming from the fan side. There's other certain reheat factors that play into it as well. The point I was trying to make was this does not include energy savings from low lift. If you were applying low lift in an office application with chill beams, you could be around 45, 50% efficiency in office spaces. Healthcare, not every healthcare application is ideal for chill beams. You're obviously not going to use chill beams in OR spaces or even isolation rooms. Where chill beams make sense is in MOBs, in administrative areas, and in patient rooms. In patient rooms, generally you can reduce your primary requirement to half, sometimes even more, based on how much your loads are, and save a lot on the reheat side of things as well. And that's where a lot of these savings come from. Same like healthcare labs, not every lab is going to be ideal for chill beams. And generally how you want to look at it is any lab where the air movement is driven by sensible cooling or the sensible load in the space. So think about your dry labs, computational labs, where there's a lot of equipment in the lab, and that's putting heat into the space. That's where chill beams can help save energy for that project. All right, so hopefully a lot of these benefits are becoming clear. Energy savings, we talked about that, reduced ductwork, reduced mechanical equipment. The three other I would quickly hit is comfort. Generally, the air leaving these chill beams is in lower 60s, which makes it a little more comfortable, less drafty for occupants. That's where comfort comes into play. Maintenance, these chill beams do not have any moving parts. So especially compared to systems like fan coils, they could be a lot less maintenance. You do need some maintenance every once in a while. You do have to go in and look at the coil just to make sure there is no lint developed on the coil itself. And that frequency can change from application to application. Offices, we see it being once every couple of years. Some patient rooms where you have certain type of linen that creates a lot of lint, you may want to do it twice a year in those cases. Quieter operation, again, because there are no moving parts, they tend to be very quiet. Generally, you could expect these systems to be roughly 10 NC quieter compared to a lot of the other systems. Some installation examples. This is overhead chill beams. You could see your ceiling chill beam exposed in the interior space, providing cooling. And at the perimeter is where you have the recess beam behind this linear diffuser with the return air coming up through the return air opening on the side here, back onto the coil on this beam itself. And this beam is providing both heating and cooling for the system. Another example, in this case, the application was reversed at the perimeter. It's hard to see, but this is where your ceiling exposed chill beams are. Whereas in the interior spaces where you're using the recess beam, there's a recess beam right here. The turner goes up this grill, and supplier comes out this grill. So the application can really depend on how you, envision the space and how you and your architect may want to design these spaces. Another example here for educational facilities, you can see cabinet beams at the perimeter. Again, like I was saying, the discharge at the low level provide displacement effect for cooling. For heating, there would be a fin tube up top that would provide heating at the perimeter, which helps decouple heating, especially for morning warm-up purposes. And also another thing I would point out is your duct and pipe risers are right here. This is where they're coming down into the beam. And then being piped and ducted to provide ventilation and cold and chilled water into these chill beams. Patient room example, typically what you would see is, a chill beam installed directly over the patient bed. That's an ideal place to put a chill beam. And typically you would need either a 4 or a 6 foot chill beam, one per patient room to provide mixing and, conditioning for the patient room itself. Labs, this picture, like I said earlier, that you can see this lab has some fume hoods, but it's not a fume hood intensive lab. What's driving the air movement is the equipment that's adding a lot of heat into this lab. So that's where chill beams made sense for this application. Now the next question is, how else could we create decoupled sensible cooling systems? Chill beams is not the only way. There's other ways you could do it. One example shown here is DOAS sensible fan powered boxes. Essentially what it is a chill beam with a fan and a VAV damper built into it, which allows you to modulate your air and provide some flexibility there. This is not a fan coil, I would insist, and it's a sensible cooling device designed to condense at the coil. Next question would be, how do you apply these? The good thing about these products is they both need the same type of water and same type of primary air. It's identical in terms of what's coming into these products, and you can mix and match them on a project. You may have spaces that are acoustically, architecturally, or maintenance driven. That's where chill beams could go, or you could have spaces that might be looking for flexibility in terms of needing some electric heating or more flexibility with modulating the airflow. That's where fan boxes may come into play as well. One example I always like sharing is you may have an open office area that may need, it could be a large space that may need 7 to 8 chill beams. Maybe you could replace it with a fan powered box just for the open office area, because that would help manage piping cost, at least for that zone itself. So that's a little bit about DOAS fan powered boxes. Some examples of projects. This is a higher education case study. You guys can see what they used here was chill sails. So in this case, they're using chill sails to decouple the system. It's still a decoupled sensible cooling system, providing radiated and some convective cooling, and then floor diffusers is what was used to provide ventilation into the space. And because of the combination of these systems with a ground source heat pump is what allowed them to achieve 67% energy savings compared to the baseline. ASHRAE headquarters. So this building was renovated about 5-6 years ago. It was an existing building where the facade was reskinned. That's what you're looking at here. And essentially, they took low lift to the next level. What they did was they used radiant cooling with air source heat pumps to provide heating and cooling for the space itself. And essentially, their water temperatures were 54 to 58 for cooling. Again, very low lift specific temperatures, and heating, they really pushed it down to 85 and 95, 85 to 95. I know Atlanta does not get as cold as Boston, but we've definitely seen projects in Boston and applications in Boston where you could achieve, Boston-specific heating with temperatures as low as 100, 105 degrees, with a radiant or a chill beam system. Another example, or picture from the ASHRAE headquarters space, and you guys can see this for this classroom. They had used radiant panels for heating and cooling, and then instead of floor-mounted diffusers, they used sidewall displacement to provide ventilation and latent cooling for the space itself. So that's a little bit about decoupled cooling systems, what to keep in mind, and generally what you could expect from these systems and different ways of doing it. Coming back to the Massachusetts stretch code, one of the elements in the stretch code is enthalpy recovery rate, especially when you're going for the stretch code or the specialized code. What enthalpy recovery rate is essentially how effectively your energy recovery device is recovering enthalpy, at the air system level, right? And what the code says is essentially your ERR, especially for the stretch code, when you're working with class 1 or class 2 exhausts, that you need your enthalpy recovery rate to be at least 70%. So 70% recovery of enthalpy from the supply side, from the exhaust side over to the supply side, right? Now you guys can imagine, essentially how much airflow that you bring in on the exhaust side versus the supply side has an impact on the efficiency of this system or this product itself, right? So if you have too much airflow coming on the supply side and too little on the exhaust side, guess what? That will affect the energy efficiency of this wheel, right? This wheel will naturally be able to transfer so much of the enthalpy from one side to the other because, again, supply area is a lot larger than the exhaust air itself. And that's where decoupled systems could help, because with decoupled systems, you would always have the balance. There really isn't any. Typically, there wouldn't be a return component. Your exhaust air will match the CFM of the supplier, and you get a lot better effectiveness at the energy recovery unit compared to a system where you may have a return air component which is not going to the energy wheel, and hence reducing the enthalpy recovery ratio for the wheel, for the energy wheel itself. So that's a little bit about the relevance of the Massachusetts stretch code as it relates to these systems. One other thing we wanted to share with you guys was some control strategies, and I'll go through this quickly. And I notice we're getting close to the end of our time slot here. I do want to leave at least a few minutes for questions towards the end. So 3 different aspects here. One is zone temperature control. Typically, you would control your zone temperature by modulating water at chill beams. There's a 2-way setup that's shown here. Pretty simple and basic. You've got a control valve. You adjust the control valve based on your set point in the space itself. Obviously, if you're using a 2-way valve, you have to have a way of adjusting the speed of your pump. That's where the differential pressure sensor comes into play. You use that to make sure that you're not overly pressurizing your piping system when some of these zones go into par load condition. There's other ways of achieving heating and cooling as well. For example, central two-pipe changeover. Essentially, what's happening here is you've got heating or hot water and cold water going into the zones, and centrally somewhere you have a changeover valve that decides if all those zones are getting hot water or cold water. So we centrally decide that, and then the zone, basically what the zone does is adjust the flow of that water based on where the space might be in terms of temperature control. Another way of doing the same thing is to do that changeover locally in the zone. So instead of doing it centrally, you basically have a changeover valve at the zone. So the zone decides if it needs hot water or cold water, and then also modulates it as well to provide temperature control. Another way of doing that same thing is by using a six-way valve. These six-way valves are starting to become more and more popular. What this is being able to do heat-cool changeover at the zone level, without needing two separate three-way valves. Six-way valve combines both the heating and the cooling deck, and essentially what you have in the space is a two-pipe chill beam which gets piped back to the six-way valve. So that's the water side. Talking about the air side, so generally speaking, if you go back 15, 20 years ago when chill beam systems first started getting used, most of these systems were constant volume. So the example that you see here is essentially where you have a duct system that's dedicated to chill beams. So the entire duct system is a constant volume system, and all you would do is just use a balancing damper to balance the system up front, and then all chill beams get the same amount of airflow or the design amount of airflow, and you adjust the space condition using water. You maintain constant airflow and then adjust water to provide comfort within the space itself. That's the more traditional way of doing it. Another way of looking at the same thing is if you have a duct system where you might be sharing some VAV zones with the portion of the duct that's feeding constant volume chill beams. In that case, you may want to consider a product like this, which provides auto regulation at the device itself. So irrespective of the inlet stack, it will maintain a certain amount of airflow going into the chill beam itself. And there's certain limits or certain ranges that you have to work with to make sure these products work effectively. So that's the constant volume side. Demand control ventilation is something that's becoming more popular, again, especially with these newer codes and the stretch code requirements. So common perception has been that chill beams are constant volume only, and that's not true. What you're looking at here is the same exact beam selected for two different airflows. If the design airflow was 125, you can see that the chill beam could be modulated to roughly half that airflow and still provide induction and heat transfer and mixing within the space itself. So that's very possible, and essentially how you would use demand control ventilation is, for example, if you were looking for CO2 control in the space, you could use a VAV box that's feeding a bunch of beams within a given zone and use CO2 to modulate the airflow going into the chill beams itself. Another way of doing the same thing, we see it more commonly in schools, is where they want to adjust the airflow or shut the airflow down or bring it to minimum based on the square footage when there's no one in the classroom for school. So it's occupancy based, right? So you have a motion sensor, there's no motion in the space, you basically have a two-position damper that goes to minimum just so there's not excessive airflow going into the classroom. So those are a couple different ways, and those work better for larger zones. What we also are starting to run into is how do you provide VAV control or demand control ventilation in smaller zones? That's where inbuilt VAV controls come into play. What you're looking at here is a chill beam with an inbuilt VAV controller and damper. And essentially what's happening here is you basically have a pressure transducer that's measuring pressure at the beam, right? And typically, as chill beam manufacturers, we would have airflow curves that tell us what you could expect in terms of airflow at a given pressure in the beam, right? And that's what we use to program these controllers. So once the controller knows what pressure there is in the beam, now you could tell, what the airflow is. And then you can adjust that airflow based on, what the requirement for the zone is. Typically, we would recommend selecting at the higher end of the static range. So for example, a typical static range for chill beams is 0.2 to 0.75. What you would end up using is the higher end of the range, 0.75 to 0.50, because that's how you make sure you have enough room to go further down to provide modulation when you're using a system like this. So that's air. Talking a little bit about condensation, there's multiple ways you could monitor space humidity and condensation in the space. And it could be a proactive way, for example, looking at the RH and the dew point in the space, or it could be a reactive way where you're looking at the condensate at the beam itself, right? What we typically recommend is, there's no right and wrong. What we commonly see is return air monitoring per floor. So you would have at the return air, you're monitoring your dew point, and that's how you make sure that the space is being monitored and is in control. Or you could have a hybrid strategy or a mixed approach depending on what's happening within the space, right? So for example, what's happening here is this was a space that had a window, right? So it has a condensate sensor and a window sensor. So what's happening here is as the window opens, the chilled water to the zone shuts off, but it does not come on just because the window closes. It's keeping an eye on the dew point in the space, and until the dew point of the space recovers, it's not going to bring the water on into that zone. So a good example is an application like this. This was at Wayne State University in Michigan. You can see there's operable windows. That's what they're using here. As the window opens, there's no water going to this chill beam. As the windows close, the system is still keeping an eye on the dew point in the space, and the water does not come on until the space has recovered. And the good thing is your air could still stay on because the air has all the latent capacity. It will dry the space up as you wait for the space to recover and bring the water back on. A couple of the things I would point out is, based on your monitoring strategy and what's happening within the space, you could do two different things. You could, control the temperature of the chilled water, which is usually done at the system level. So if you were monitoring return air at the floor level, what you would do in that case is adjust the temperature of the water up at the chiller level in case if the space was to, space dew point was to rise, right? You basically adjust your chilled water temperature accordingly. Or like the previous example, if you're doing a shutdown, chilled water shutdown, then you would do it at the zone level because that's what makes more sense. Your problem is more at the zone level than being at the system level. A couple examples. In this case, you can see there's no open ceiling. It's an open ceiling application. There's no ceiling, which means the entire space is seeing conditioned air. So typically, what you would do in these cases is just monitor return air, and that should be enough. In a case like this, again, typically just monitoring return air will be fine. If you wanted some more belts and suspenders, because there's a closed ceiling here, you may want to have a couple condensate sensors on either end of the floor, just to keep an eye on those in case if things were to go out of control above the ceiling. And last but not least, these control strategies have been applied very successfully for a long time, so you should have some comfort level with it. What I wanted to point out was condensate does not happen instantly. This was a study that was done to study just exactly these systems. What they found was with a delta of 14 degrees, so your dew point in the space was 14 degrees higher than the surface temperature, it took 8.5 hours for the water droplet to get to this point where it would drop into the space, right? And the point is, condensate does not happen instantly. There is time to react, which you're not relying on it. But just because your dew point slightly went above, the set point, doesn't mean it's going to start to rain. You're going to have a lot of time for the system to recover and react as need be. Facility training is always very important. Air handler dew point, we talked about that earlier, and also all the sensing that we talked about that earlier as well. So to wrap it up, the big takeaways would be, low lift is what gives you higher COP, so do consider that on your projects. Sensible heat ratio is a good indicator of where decoupled sensible cooling systems could be used, and that's what's listed here, 0.7 to 0.9, and those applications are listed there. Condensate formation is not instantaneous. It takes time, and there's multiple ways to take care of it. And last but not least, there's many different ways you can create sensible cooling systems, and all of those are shown here. depending on what works the best for your project is what you need to look at and apply on your projects.